Hello, I'm Stephen Harrison of Harvard Medical School, Children's Hospital Boston, and the Howard Hughes Medical Institute. This is the first of 3 lectures on virus structures. This first lecture will be about general features of the molecular organization of virus particles. The second 2 will be about specific properties of virus particles relevant to the molecular mechanism of infecting a cell. Viruses are carriers of genetic information from one cell to another. In that sense, they're effectively extracellular organelles. The infectious virus particle, sometimes called a virion, is a molecular machine that packages viral genomes, escapes from the infected cell, survives transfer from one cell to another, and attaches, penetrates, and initiates replication in the new host cell. It's thus not just a package, a passive package, but rather an active payload deliverer. Now, most people know viruses as pathogens because the virus bears the genetic information needed to usurp the cellular biosynthetic machinery and replicate itself. The selective advantage for evolution of the virus may be a selective disadvantage for the host. And as a result, hosts evolve defense mechanisms, the immune system in the case of humans and other higher vertebrates. Now, viruses come in 2 major flavors. Envelope viruses, in which the infectious virus particle is surrounded by a lipid bilayer membrane derived from host cell membrane, and non-enveloped viruses, rather unimaginatively, that have no lipid bilayer membrane and the protective coat is just protein. These 2 structural modes correspond to different modes of exit and entry into cells, different mechanisms of assembly and different mechanisms of infection, as we'll see in the course of this lecture and the next 2. Now, just as quick examples, on the right is an example of a non-enveloped virus particle, a rotavirus particle. This image is based on reconstructions from many electron micrographs, and we'll go into that in some of the details of that in the 3rd lecture. And on the other side is an example of an enveloped virus particle, also studied by electron microscopy. And in the cross-section of the image that you see at the bottom, you can clearly see evidence of the lipid bilayer with alpha helical segments of the protein on the outside traversing it. Just to remind you of sizes and distances, both the rotavirus particle and the Synbis virus particle, as the right-hand one was called, have outer shells that are about 700 angstroms in diameter, or 70 nanometers. That's about 1/1,000,000th the size of a tennis ball. Recall that chemical bonds are between 1 and 2 angstroms in length, and that's why chemists use angstroms rather than nanometers. It's the natural unit of a chemical bond. So when I say 700 angstroms, you can think of that as 500 to 700 atoms across. Of course, it's a volume, and so the molecular mass of these particles is some tens of millions of Daltons. So bear in mind during this lecture the following 3 questions. We'll talk about more than just these 3, but the main point of the lecture will be to try to introduce you to the following issues. First, why most non-enveloped viruses and a number of smaller enveloped viruses have highly symmetric structures. Second, what do the building blocks of these particles look like? Turns out that the same kinds of building blocks have been used over and over again in the evolution of different viruses, even viruses with very different replication strategies. And finally, what do the outer proteins of some envelope viruses look like? So let's begin with symmetry. What does symmetry mean? Symmetry, as suggested by the image on the left, means that there's some operation, in the case of physical objects, some physical operation like a rotation, that brings the object into self-coincidence. In this case, if you rotated this figure by 120 degrees about the axis represented by that triangle, and you closed your eyes while you did it, you wouldn't realize that you had done the rotation. That's called a threefold axis, and as you can imagine, symmetry of more complicated objects can have other symmetry axes, and so the icosahedron, we'll come back to that in a minute, represented on the right, has fivefold axes, threefold axes, and twofold axes.